Okay, complex numbers. Anybody who doesn't know what complex numbers are would look at this and say, ooh, that's complex. No, actually it's not. What is a complex number? A complex number is a mix of real and imaginary. What you see there is not complex. It is a mix of something and something, not real and imaginary. Can you remember what these kind are? This is one of those topics for the ACT. Do you know the difference between real and imaginary? And do you know the difference between those two, which isn't a real and imaginary thing? Can you remember the name for it? Yes, sir? You are correct, sir. Rational and irrational. Okay. And the official definition of rational is rational numbers can be written as a fraction. Do you get when you have a square root of something that doesn't work out nice? Like square root of 5 doesn't work out nice. Then you can't make a something divided by something for it. Like 3. 3 is rational. I can make a fraction for it. Root over 1. 0.7 repeating even though it's kind of complicated, it's still rational because I can make a fraction for it. Anybody get that one memorized? 7/9. Good. 0.78 repeating. 78 99 does that one. But the point is, those are all rational numbers because I can make a fraction. But a square root, unless it happens to be of a nice one like that, that's really just 4. And then you can just write it as 4 over 1. Okay, so that's still rational. But when you get this, square root of some number that doesn't work out nice, you can't make that into a fraction. All right. So why does all this matter? I just want to make sure you understand that a complex number is not just a complicated number. A complex number is actually not a mix of rational and irrational. A complex number looks like this. It's a mix of real numbers, which can be rational or irrational, and imaginary numbers. You remember the I? All right, so we're going to basically talk over that again. And today's the first day, and we're not going to get super deep into this, so you won't be doing super complicated things. But one thing I really do want you to work on this 3 plus root x over 2 minus root x. And I want you to just think through, like, what's wrong with it the way it is? Why can't I just leave it alone? Well, dividing has rules. Like, what's one of the things you can't divide by? 0. And square root's another one. 0 is the big one. Can't divide by 0. But you also can't divide by square roots of things unless they turn out perfect. Okay? As in, you can't have an irrational number in your denominator. So how in the world are you going to get that out of there? Hint, you're going to multiply this by something. And somebody's going to remember this from trig. This is a review again. You did this before. Who knows the word for it? It starts with a C. Conjugate. Nice. And if you remember what conjugate is, that would be even better. Do you know that part?
Yeah, you just multiply by that.
So 2, what?
2 plus.
You are correct, sir. And if I multiply that on the bottom, I got to do the same thing on the top. Remember, to keep this fair, I got to do whatever I do on the bottom, I got to do it on the top. Now, multiplying that all out seems really messy. That's what today is like. It's multiplying things out and kind of cleaning them up. There's a lot of that. All right, so why is the conjugate good? Because when it's done, if you do this right, you will have gotten rid of the square root in the denominator. You still have one on the top in the numerator, but you won't have one in the denominator. Go ahead, multiply this out. Take the time to grind it out, clean it up. And one thing that's going to come up that's really important is this. If you have the square root of x times the square root of x, do you get that's just what? X. It's whatever, it's not the square root of x. Think about it. You take the square root of x and times it by something. It can't be the same. It's not the square root of x, it's just x. I'm going to pause for a minute while you grind that out. All right, we're back. And hopefully you just did first outside, inside, last. The first here would be 3 times 2 is 6. The outside is 3 root x. Inside 2 root x makes a total of 5 root x. And then the lasts make x. All over the denominator, which works out nicer. Why? Because it's the conjugate situation. This and this are specifically conjugates, which means that their middle term blows out. The first is 4, and the outside and the inside are opposites, so they're gone. And then it's just plus x. There we go. Raise your hand if you had that one right. Oh, what did I do wrong? Oh, it's a minus, sorry. All right. All right, so any questions on that one? Okay. Now, how is today like that? It's exactly like that, except it has i's in it. If I have 1 over 4 minus I, that is a complex number, and it's in a fraction. And just like dividing by 0 is bad, dividing by square roots is bad, you can imagine dividing by I is bad. So how in the heck are we going to get that out of there? We are going to multiply the top and the bottom by what? 4 plus I. 4 plus I. But in a moment, we'll do that in a moment, because I want to stop for a second and just remind you, in case you've forgotten, what the heck is I? It comes up because if you have the square root of negative 144, you can actually get an answer instead of just saying, oh, that's not possible. We have to be able to go beyond just saying, oh, the answer isn't real. Okay, it's not real, but you can still get an answer. And why would you care? Other than just theoretically, there is things in math that are just theoretical, but this is actually in the real world. If you look it up, one of the uses for negative square roots, or the uses for imaginary numbers that happens in the real world, is if you were an electrical engineer and you are doing a complex calculation that figures out about electricity flowing through, lines and stuff, there are equations that use imaginary numbers, but yet you need to use them to get real answers for real problems with electricity. I can't explain the exact details, and even if I was an electrical engineer, you probably wouldn't totally understand it anyway. Just trust me to say that it isn't just theoretical. You actually need this branch of mathematics to be able to handle some real-world problems. All right, so I hope you get this is the same as the square root of negative 1 times the square root of 144, and that part works out nice. It's just 12. And this part is defined as I. So the answer is 12I. Raise your hand if you already knew that. Okay, good. Then, do you know that a I squared is something important? Remember, raise your hand. Don't say it. Raise your hand if you know what I squared is. Okay, so the 8 of you had that advantage on the ACT. The ACT, when you take it, is very likely to have an I on it. I heard that this year's ACT had an I on it, for example. And if you don't know what the heck it is, and you've got a big disadvantage, right? And from what I've seen, 9 times out of 10, in the problem, they end up doing something to the I, so it ends up having an I squared in it, which is equal to something simple. Is it 1 or negative 1? Negative 1. And here's why. Would you agree this is the same as I times I? That's pretty obvious. And I is the square root of negative 1 times the square root of negative 1. And didn't we just learn a second ago, or remind you a second ago, that no matter what that is, let's say it was x, the answer is just what's underneath the root. I just want to really clarify that. Square root of 7.03 times the square root of 7.03 is really easy. It's what? 7.03. Okay, it's whatever's under the root. So that's why this is equal to negative 1. So I squared is negative 1. Now, this is where it gets a little weird. If I is the square root of negative 1, I squared is negative 1, what's I to the third? I want you to prove what you think the answer is. Prove it by showing me how you would get it. I'll pause for a moment while I give that a try. So for instance, something like I to the 9th would be a whole bunch of I squareds, like I squared to the How many I squareds do you want? Do you really want to write out a gajillion I squareds? No. I squared to the 4th, that would make 8, and then we need one more I. And do you get how that's really just negative 1 to the 4th power? What's negative 1 to the 4th power? 1. 1 times I means the answer is I. Whoa. Hello. Sorry, something fell off my board. All right. So if I to the 9th is really I, isn't this weird? You take something and you put it to a power a whole bunch of times and you get the same thing back again. Can you name anything else that does that? 1 does it, but this is different because this is different things along the way. Sometimes it's negative I, sometimes it's negative 1, sometimes it's I, sometimes it's negative I. And so there's a pattern. I'd like you to figure this pattern out by doing I squared, I to the 3rd, I to the 4th, and I to the 5th, and I think you will see the pattern and how it starts to repeat. Pause for a second while you try that. There you go. I is just I. I would have accepted I, or I would have accepted the square root of negative 1. And I squared is negative 1. I to the 3rd is like this times this. So it makes negative I. I to the 4th is like I squared, which is negative 1 squared, which is positive 1. Those are 4 completely different things. And then I to the 5th comes back to I again. Do you get that it's starting the cycle over again? And it'll repeat the cycle of 4 things over and over and over again. But you don't need to like memorize exactly what the cycle is and everything. All you need is these two. Because if you know I is square root of negative 1 and I squared is negative 1, you can make anything. Like, how about this? I to the 301st power. It should take you about 10 seconds to figure out what that is. It's a bunch of I squareds. And a little bit more. I'll pause where you figure that one out in the video. Okay, so one of my students was having trouble figuring out what this means. And I was helping him by saying it's I squared to the something, a whole bunch of I squareds, and then that would be an even number. And this is an odd number, so we need one more I. So really it just boils down to I squared to the what? 50, not big enough. 150, I would buy that. There we go. And then what is I squared to the 150th power? Well, that's like saying what is negative 1 to the 150. Since that's an even number, right? Ends in 0, it's even, right? It's an even number. They all cancel each other. It makes positive 1 times I, so it's just I. And there's the proof. Raise your hand if you would have had that right. Okay, good. Now, that's one area you'll have to be able to handle. Covered that. Let's move on. Let's say that you had this. X equals negative b plus or minus square root b squared minus 4ac all over 2a. Why am I bringing this up? In the context of negatives that are under square roots. When you're solving a quadratic, do you get sometimes you have to use this beast? Do you get that sometimes? You get a negative underneath the square root. What does it mean? That means the answer isn't what? Real. What does it mean in the context of my parabola? Could that be the graph of it? No, because that one would have what? That would have x-intercepts. How many? That would have 2 real answers. But what if I put it up here? Could that be my answer? If it's got a negative under the square root, yeah, it looks something like this. It means that it doesn't touch. Because if it touched like this, it wouldn't have had a negative under the square root. If you got a negative under the square root, you got an imaginary. If you got an imaginary, that means your graph isn't touching and therefore doesn't have real answers, but it has imaginary answers. So imagine for a moment that you had 2 plus and minus the square root of negative 25 all over 10. I would like you to simplify that down with what you know about imaginary numbers. You should be able to simplify it down to like 1 plus and minus the square root of 3 over 2 or something like that. It's not right, but simplify this for me using imaginary numbers. I'll pause for a second while you give that a try. All right, so I agree. 2 plus and minus, that's 5i over 10. But did you know how to go further than that? Yes, you could, but that's not what I'm talking about. You could write 2 separate equations, but we don't need to do that. Can I just cancel this and this? No, I can't. Why not? That adding and subtracting thing in the middle of the problem means I can't. So, again, another thing that people like to do is cancel the 5 and the 10. I'm going to cancel those two. No, same reason. You're in the middle of an add problem up here. You can't do that. What if that top part would factor? But it doesn't. If this was like 10 here, then I could factor a 2 out of the top and a 2 out of the bottom, and then I could cancel stuff. But bottom line, that's right. It's the answer. You don't have to go any further. Now, could you write it as 2 separate things? Sure, but you don't have to. Yes? 2. That is a good question, and it is a very good question, in fact. 2 over 10 plus and minus 5i over 10. Can you do that? Think of it this way. Both of these got to get divided by 10. Did I do that? Yeah, so that is a good thing to know. Why? Because now it can be simplified. Now this part can be simplified. It's just 2/10, which is the same as what? 1/5. If I wanted to do this as a 5 times 2 to show the 2's canceling, it's 1/5. Plus and minus, now these can simplify. I over 2. We do agree that'd be the same as 1/2 I. I over 2, same as 1/2 I. Why would this be better? Because it's separated into the 2 parts. Remember me saying there's a real part and an imaginary part in a complex number? This is the real part, no i's. This one, the imaginary part. So that is a good idea, and I'm glad you brought it up. All right. So now, let's do one more like that. 6 plus and minus the square root of negative 36 all over 2. Remember this from the top 20? It's just a tweak off the top 20. In the top 20, there's no negative under the root. But you have to be able to handle that. Now, you can factor it. You should. So I can factor out a 2 and get 3 plus and minus 3i over 2 and cancel them. And other people are going to say, well, I wanted to split it into 2 parts, but didn't you end up getting the same thing anyway? If you took this part and then this part, you'll get 3 plus and minus 3i, and it's the same thing. So I just like to think of it as factor the top part and then stuff cancels. All right, this is a complex number because it's got a what part? Real part. And a what part? Imaginary part. All right. Now, there's one more little thing that just called about terminology. When we name these things, we don't say f of x because they're not functions. If I'm going to name one, I'm going to call it just like z. I give it a name like that. And then let's say I had another one. You know, like we normally say f of x and g of x. Well, I'll say z is this and t is this. Do you get if they go like this, what's z times t? They're just asking you to multiply those two things. And then you just FOIL it out, first outside, inside, last. Guess what you'd have in it for sure? I squared. And when you have that I squared in it, you pull it out and replace it with a -1. And that's the most common ACT kind of question that I've seen is they give you this situation where you got to multiply these two numbers. I'll give you an example in a picture. Let's say they gave you this and they said this is 3 plus 2i and this is 4 minus 3i. What's its area? Well, basically that means do that one times that one. So go ahead, multiply them out and tell me what you think the answer is. They would probably have to put in some kind of clarifier that in the imaginary number system, this square has an imaginary area of what? Because I think it's going to have an I in it. In a moment, I'm going to ask you to compare with the kid next to you. So, do a quality job on this. Write out, and I think your answer is like 6 minus 4i or something like that. Okay, I'm going to pause while you give that a try. Okay. What did your group get? A little louder. 6 minus I? All right. Did anybody get the same thing? Okay, what did you get? 18 minus I. Did anybody get 18 minus I? Oh, a whole bunch of hands. All right, let's make sure we see y. That times that was 12. Outside and inside give us our, let's see, -9 and +8. That makes our -I. And then the lasts, which would be this times this, give us -6i squared. That part should be -1, which makes 12 minus I minus 6 times -1, and that makes +6. And that's where you get your 18 minus I. Did you figure out where you messed up in it? Okay, this happens. All right, so that is a typical homework question for today, and here's one more that's similar. Let me show you. Let's say I said, what's z times z with a line over it? I want you to just take a guess. Just take an informed guess about what the heck z with a line over it means. Come on. Yes? Close. No. Yes? Nope. Good guess. That is repeating in other forms, but this does not mean repeating here. Nope. Good guess, but not right. Yes? The conjugate of z. Very good. So z, which is 3 plus 2i, times the conjugate of z, which is what? 3 minus 2i. And I want you to get what conjugates do again. The first is 9. The outside and the inside cancel. That's the whole point of a conjugate. So they're really quick to do. And then the lasts are 2i times -2i. What does it get? What does it come up to? 2i times -2i. 4. First of all, just don't simplify it all the way down. First of all, it's -4i squared. And then the I squared turns into -1, and then that's why it's +4. And do you get that that one actually worked out really nice? So it's really just 9 plus 4, just 13. Unlucky number, but nice simple answer. Raise your hand if you had that one right. Okay, good. So that is your basics. Let's look at the homework together. Everybody find it. I'll pause while we find it. Okay, so that's the final tip I have for you, and that's all that I have. Actually, I should probably tell you which problems we did, just in case you're at home. Here's the problems that we did today. We're doing the first page here, the pink page, all of them. Here we are skipping D and E. Those are the only ones I want you to skip. And then doing all of these, and then we're skipping 19, 20, and 21. And I gave them a little help with number 23 there. That's all I got for you for today.